To tell you a little bit about our Suspre University ion implantation calculator program, Suspre. That's just been revamped as a Windows 10 application, which you can now download from the UK National Ion Beam Centre website. I'll just give you some background about the program and then tell you where to get it from. Okay. So Suspre very quickly can calculate ion ranges, can calculate energy deposition profiles, and from the energy deposition profile it can calculate sputtering yields as well as damage profiles and look at what happens in accumulated systems as well as the dose becomes higher above the solid solubility limit too. It does this all very quickly, so it can be used like a calculator. That's its primary purpose. It does this by using what's known as the projected range algorithm, which is an algorithm dating back to 1980s, which is based on the Boltzmann transport approach, which just assumes that essentially that an ion arrives at the surface, or a set of ions arrive at the surface with energy E0, so they're all monoenergetic when they arrive, and gradually they spread out as they penetrate through the solid. Through the solid they get more spread energy, and when they get to the point where they have zero energy, that's where they stop. So ultimately we end up with a range profile where all the particles that are spread through the solid have all ended up with zero energy, and from that we can calculate effectively, very simply, the range profile. And the projected range algorithm actually produces a set of moments that describe that end point where all the particles have zero energy. And it gives us two moments particularly, which is the range and the standard deviation, the x bar and the sigma. And the nice thing about the projected range algorithm is it's very quick, so it produces these values very fast, but it also is pretty accurate as well. It's quite close to other techniques of the Monte Carlo program SRIM. It's very close to the Monte Carlo program SRIM in terms of the values it gives for the range profile, RP and the sigma, and it's also very close to experimental values as well. So this is quite useful to be able to predict these things very quickly and very simply. The projected range algorithm to calculate where the particles are stopped. So it tells us a little bit about how the particles lose their energy as they go through the material. But Suspre does a little bit more than that. It doesn't just work out how our particles lose their energy, but also where they deposit their energy. So it does this by looking at the way in which the energy is partitioned differently due to the recoils in the cascade as well. So the recoils themselves spread out the energy in the cascade throughout the solid, and that gives us a little bit slightly different distribution from just looking at where the energy is lost just by the ions. Allows it to spread out. And we use the intermediate energy profiles that we cut through the axis of the way in which the particles slow down. We get a distribution of the ions that have specific energies, and we can use that to actually to tell us where the energy is actually being deposited, not just lost to the sample. We assume the spread of the energy loss is going to be linear with depth, so it starts off monoenergetic at the top and then spreads down to the Gaussian profile when the energy is zero, and as we spread down that we gradually linearly spread out the standard deviation effectively with as the depth increases. That makes it much easier to calculate and quicker to calculate things, and it's not an unreasonable approximation to make. If we look at the bottom right hand corner there, the 140 kV silicon in silicon, we can see when we do it properly the spread is pretty linear. If we do it with the very low energy 1 kV silicon in silicon, then we can see that it's not quite so linear and there are some errors involved in that. So very low energy, we're going to get into a little bit of an issue at the with the energy loss deeper into the target, but at the very surface region, which is important for sputtering, then that may be less of an issue. So how well does it work? We did some comparisons, particularly for the sputtering yield, looking at the yield versus energy for a number of different ion species. and compared those with experimental values in the literature. And we can see that the fits are pretty good for these particular iron species. We've got the absolute value of the sputtering yield is coming out pretty close for the majority of things, up to 60 kV or so, which I think is quite encouraging. We also looked at over 600 different experimental values and plotted the ratio of the simulated yield to the experimental yield. We'd expect obviously that to be 1 if we were doing very well. We plotted that against the ratio of the mass of the iron to the mass of the target, and we can see that along the line there's a very good agreement with a value of 1. Obviously there's a little bit of difference. This is probably due to either experimental error or just errors in the stopping powers in general, which are never going to be that perfect. But I think overall it shows very good agreement, at least enough for a calculator. If we look at damage profiles, and if we look at the range profiles, we compare those to SHRIM or TRIM. We've got 140 kV silicon in silicon, 120 kV antimony in silicon. 20 kV and antimony in silicon is really quite almost indistinguishable from the SHRIM results, so that's a good sign. The 140 kV silicon in silicon is not too bad either. The range profile is pretty good, and the energy deposition and damage profile is encouraging as well. As yet, Suspre doesn't include layer structures, but there is a formalism for doing that within the Suspre framework, which we demonstrated some time ago, and one day we might put that into SHRIM as well when we get to version 2. So maybe that's something to look forward to. What we've demonstrated is that Suspre is quite a versatile little program for rapid calculation of range profile and sputtering yield data. It's quite quick, which is useful for it, and it can act like a calculator in that sense because it's quite quick to change parameters and just see how things go. So for trends, I think it's quite useful. For absolute values, it may be a little bit less accurate. And never will be a complete replacement for experiment, but I think within 10, 20, 30% or so of values we can expect it to work quite well, apart from where perhaps a lot of chemistry is involved, in which case we've got no chemistry built into the program, so we wouldn't expect that to work that well. If you enjoyed it, then it's available on the website at uknibc.co.uk/Suspre. You're welcome to download it.